Good morning, good afternoon, and good evening. This is our first webinar of the year, and we want to thank you all for joining us and let you know that we greatly appreciate you taking time out of your busy day to join us. I'm Tom Concolino, and I'm here with our presenters, Aya Takase and Angela Criswell. Thank you all for attending Rigaku's webinar series on X-ray computed tomography for materials and life science. This session is on micro-CT data collection techniques, and it will focus on the data collection methods for routine micro-CT analysis. This session will be taking place in the lab with Angela and I are reviewing in real time how to develop a scan for a variety of sample types. They'll also be offering their thoughts on dealing with unique challenges of performing CT experiments on material science samples. Please note, if you missed any of the previous webinars, you can view them on the Rigaku website. Before we start, a few housekeeping items. As far as today goes, we're going to be doing things a little bit differently. So this is going to be an interactive session. So we'll be taking your questions live during the webcast, but we'll be answering them during the session. So please don't wait until the end to ask. And as usual, please submit those questions via the Q&A button at the bottom of your screen. I won't be monitoring the raised hand function, and I'll be posting relevant links in the chat window. We'll be trying to answer as many questions as we can during the webinar, and we'll respond to any unanswered questions directly after the session is complete. So if for whatever reason you have difficulty viewing the webinar live, please note that it is being recorded, and you'll be able to view the recording beginning tomorrow. And with that said, I'll turn it over to Angela and Aya.
Thanks, Aya. Thanks, Tom. And thanks to all of you for joining us for this presentation, the workshop. Today, we're presenting live from our office in the Woodlands, Texas, just outside of Houston. And we're going to be doing a live demonstration on micro-CT data collection techniques. And we'll be using Rigaku's CT Lab HX instrument. And so we're going to take a quick look at that instrument, the interior, and then I'll show you the actual instrument in just a second. So here is what the instrument would look like if we could see inside of it. So you have an X-ray source. And with regard to the X-ray source, we're going to consider things like X-ray energy, filters going along with that. We're going to be considering focus size and how that might impact some of our settings. Also inside the instrument is a sample stage. It moves and its position will change with the field of view, as will the detector, which is also movable. So the things that we're going to be looking at, like I mentioned, we're going to consider X-ray energy in our first example. Our second example will ask questions about sample orientation. We'll look at sample holder material. And our fourth and final example will be considering the field of view versus the resolution. So I'm going to move on to the next slide, and Aya is going to introduce the samples as we go along. But to make sure that you can see, I'm going to move over the camera view as she does that. So you should be seeing the instrument now along with that.
Okay, so Angela is going to get the first sample, which is this Apple plug. So let's think about what condition we should be using to scan this sample, which is a combination of a plastic and some metal parts inside. So instead of Angela showing you what we should be doing, I'm going to ask you a question. So let me start the polling. So which filter and data collection setting is best for this sample? This Apple plug, plastic and a metal. We could use either no filter and 60 kV setting. She's showing you how big the sample is. Okay. And you could use maybe copper 0.2 millimeter filter and 130 kV setting. This 130 kV, by the way, is the voltage you can apply to the X-ray generator. You could also use aluminum 1 millimeter filter and 90 kV. It's pretty split, actually. We'll see. I'm going to give you a few more seconds to think about it. So Angela is showing you different filters you can choose from.
Okay. And I also showed you that the sample is 50 millimeters.
The 50
so
millimeters.
that's going to
Okay.
be our field of view.
Okay, so I'm going to close the polling and show you the results. So it's kind of split, but looks like copper 0.2 millimeter filter and 130 kV is the winner. So she's going to use that set of conditions.
Okay, I'm just going to show you how I put that in here. We're going to just have a quick look. I'm going to move my camera just a little bit. You'll see that I have some foam material on the sample stage where I'm going to place. It's dark, and I did that on purpose so that we can have some good contrast to see our white sample. And I'm going to place this filter material right here that's just downstream of the exit window for the x-rays. So let's make sure it's in place. So you should see it there. And then next, what I'm going to do is I'm just going to place our Apple plug on the sample stage, the center, right? And before we measure this particular sample, we want to make sure it's centered in the X-ray field of view. So
we call it an Apple plug, but I'm not sure if that's a technical name for this.
Right. I can verify that that one was purchased from the Apple store. So.
Looks like it.
Yeah, I had another one, and it's less complicated inside. So.
Oh, it's different.
It is different. So now what you should see is an instrument panels that we use to collect data. And here is the control window. And from this window is where we would set the applied voltage. You chose 130. I know that things inside are fairly small, so I'm going to use a medium focus. If they were really big features, then I could crank this up. That's going to impact what our applied current will be. The smaller the focus size, the lower the current setting. And our field of view is 50 millimeters. So let's just have a quick look. All right, it's a little low. We're going to pick it up just a little bit. We can rotate that around just a tad. Make sure it stays in the field of view. It's a little bit off to one side. We can move that a little bit. And away we're going to go with our measurement. Okay, so we can track the progress of this measurement by looking at the rotational control in degrees. It's going to rotate from 0 to 360 degrees to 29, 30, and increasing right now. We can also watch this field. So it's basically 2D radiographs that are collected along those degrees. And then finally, we can have a look inside the instrument, and you can see the Apple plug here that's rotating.
I think we're getting some questions, right?
Yeah, yes, we did. So
okay.
We got a couple of questions really quick. The first one was from Roger. Do you need to do anything to change the power settings beyond clicking the pull down tabs?
You don't. This instrument is intelligent in the sense that it's going to make the adjustments to the current for you to minimize it whenever you decrease the focus size. It's also going to impose some limits so that you don't hit things inside, so that you don't have collisions, rather.
Okay, all right. And then the second question here from Richard is, what's the target X-ray source for this instrument? And you're probably gonna answer the second question is, why did we choose the aluminum filter?
Oh, did we? Oh, okay. So in this case, did we choose the aluminum filter and I put the wrong one in?
You chose aluminum, but the audience chose copper.
Yes.
I did. I put copper in. So we definitely put copper in. So
okay.
this is a tungsten source. I'll just make sure I didn't make the wrong decision.
That's
this is our first live session, so
because I still have the aluminum filter here.
Okay, so the copper is in there.
Copper is in there.
All
sure.
right.
The display is not right.
Oh, yes. I didn't choose the drop down. So that gets saved to a database so that if you come back and visit your scans later, then you'll know how it was collected.
Mm-hmm.
All right.
So it's returning back to 0. That's a really good catch.
Yeah.
That's something I should have caught. So if I came back later, I would be under the mistaken impression that I collected it using an aluminum filter rather than the copper. And that's just a drop-down choice as well for whichever filters you have.
Yeah.
All right, so it's returned to 0.
So we've got one more question actually while it's going through the reconstruction. And it's, you know, so there was a little bit of the sample outside of the FOV. How will that affect the reconstruction itself?
Well, we won't see the full sample itself. Basically, whatever's in that bounding box is what's going to be included in our reconstructed image. So if I were being really careful, I would have opened and maybe repositioned it quite a tad. But for the purposes of this illustration, it won't matter. But you're right, you should be careful when you place a sample. My graduate advisor used to tell me, he says, well, if you put junk in, you get junk out. So you got to consider all the settings that you're using. All right, so it's finished reconstructing. And I know that because this window in the bottom left-hand corner is closed. And here we go. This is our reconstructed view. So I can zoom in here and I can translate this over a little bit. And we definitely see some features happening within the X-ray image itself. So for example, we see these streaks here. We don't see them so much around the metal parts, but for the metal parts that are inside, we're getting these what are called metal artifacts. And it turns out that for the purposes of this experiment, you did choose the correct condition or the best condition of the ones that we gave you. But let's ask the question, what would it have looked like using something else? So just confirming, you can see the other screen now. And
we see the slide.
Yes. So if in fact we had measured data using 50 kV and no filter, you can see how terrible it really is. So there's much more of the metal artifacts coming through. If you use an aluminum filter, it's a tad better. However, with the copper filter, it's even better. So that's the right condition. And in fact, we might try a number of different filters or settings for our final image. Okay, so I'm going to move on to the next example. And I'm going to have, or first let's do side by side. This makes it pretty clear now, doesn't it? So as there is some improvement that's made here. And in this case, these images illustrate that really well. So on our next slide, I'm going to get our sample ready. And while Aya tells you about it.
Okay, let's switch to the camera so that we can look at the sample. There we go. Thank you.
And I am just going to grab that sample.
Which is 3D printed plastic. It's, I guess, about 2 inches wide, cube shaped roughly. So this is a kind of box or cube shaped plastic sample. And the next question I'm going to ask you is, which orientation will result in the best image? You can just, without thinking about it, put this cube shaped sample on the stage, either horizontally, vertically, or maybe you can tilt it. Which one would work the best? It looks like a lot of people know how to do this, right?
Very clever.
This is an easy question.
Yeah.
And some of you might have been in the convention we did last year because we talked about this one. Okay, so let's take a look at the results. Gonna end the polling and show you the results. Tilted is the winner. So we're gonna do this tilted.
Okay.
Okay.
All right. So I'm gonna go back to our instrument panel here. I measured the sample. So remember, you need to know the sample size to select the correct field of view. It's pretty big. So it's about, I'm going to use 100 millimeter about. I am going to, in fact, change the filter for this particular sample. It doesn't contain metals or anything, and I'm going to change it to aluminum, which is a good one for this. I'm just removing the copper. I don't have to change the drop down, right? Because I've got already.
You already have aluminum, yeah.
That's right, selected. But what I want to do is I just want to switch back to the camera for just a second and show you what's going on there. All right, when I change the field of view to 100, now the sample stage is moved a bit. I'm going to take this guy out and I'm going to put this one in, and I can just simply use a piece of foam that's got a wedge shape. I've got an even smaller one to tilt this particular sample. So, all right, it's in there. Let's hope it stays. Stay put. All right.
Talking to the sample.
Sometimes I do, and I get really upset when things don't work out. So I find it helps. Now it's really off center, so I'm just going to talk to myself a bit and ask myself to maybe center these
you can use
better.
that sample camera inside of the machine to center it when you do it, right?
Right. But my field of view is a little larger than the actual block in this case. So now we want to do is we want to go back over here. Field of view is 107. I've switched focus to large. If you notice, those holes were pretty big. So I'm not looking at any fine features like I would have in the other case, but I do need to make sure I can actually see the sample in the field of view. It's going to be taller than the last one. So let's just wait for that to come up. Yep. You see that foam is pretty much transparent. We can see a little bit of the tape, but not really a lot. Some tapes are pretty absorbing, I found. All right, looks good to me. So I'm gonna set this off going and let's see if anybody has any questions.
All right, so yeah, we've had a bunch of good questions come in, and actually 3 of them are related. So I'm gonna give them to you rapid fire, and you can respond to all of them, okay? So the first question is selection of the filter energy typically a trial and error process? What factors should be considered when selection of the filter and power? Next question, again, related to filters, is can we use a stainless steel filter for the Apple plug? And then the third is, again, more of the question of configuration. Which filter would be better for ceramics? So a bunch of questions all related to, again, the beginning of these measurements.
Right. So we currently have our system set up to use the filters that we currently have, but certainly you can set it up to use other filters. I don't know that we have a stainless steel filter. Now, Aya might, and she might be familiar if something like that's been used in experiments.
Actually, we have kind of empty slots for the filters where you can put whatever material of your choice and use that as a filter. So in terms of whether or not can we use a stainless steel filter, yes, we can use one. But for this particular system, X-ray generator goes up to only 130 kV. So if you use a stainless steel filter, depending on the thickness, that can reduce the intensity quite a bit. There is always a balance between the thickness and the material of the filter. And you can use whatever you want, but when you put too much filter in it, then you lose the intensity.
Right. I mean, that's the whole job of the filter, is to filter out some of those lower energy X-rays in that first image. So leaving just the harder X-rays that are transmitted.
You're trying to shift the X-ray energy towards the higher side.
Correct. Yep.
All right.
And so I think one of the questions, was about, is it a trial and error process? A little bit, but there are a couple of rules of thumb that you're going to use. The thicker or the denser the sample is, the higher you want the X-ray energy to be. That means you want to increase the applied voltage and try denser or thicker filter for heavy absorbing samples. And when I say heavy absorbing samples, I'm not just talking about the density of the sample. It's a combination of the density and the thickness of the sample.
Yeah, so you can visit some of our past webinars and we address exactly those subjects there. So Aya does a really good job. I think it's a second webinar talking about X-ray energy and such. So that's a good one.
A third, I think. I'm sorry.
The third one.
Yeah. The second one was, yeah, I know. The second one was the data analysis.
Oh yeah. Okay. That was a really good one too. So, all right, so here's our image. Oh my goodness, it's a mess. It doesn't look like a block, but that's just because of the orientation we used in this case, right? So we could certainly adjust that. But we can zoom in and we can see that here, we see nice surfaces here on all of them. And that's because you chose the correct answer. So tilted was correct for this. But let's look at what happens as a consequence of the position if you chose, for example, vertical or horizontal. So we're going to go back to the other screen real quick. You see the camera there, which I've moved back. And this is the horizontal. And so here you see this beam hardening effect on the sides of the material here. If instead you orient it the other way, then those beam hardening effects are shown here. And this was the tilted one. Now it doesn't look tilted because in the reconstruction program, I can basically rotate the tomogram in 3D so that you can see it a little bit better. So here they all are three together. And you can imagine that if you just printed this and you wanted to compare it to maybe a CAD model, you'd want to be able to identify the surfaces of this material well. And these are quite blurred in the cases of the vertical and horizontal, but they're very nicely resolved here in the tilted. Okay, so congratulations, you're 2 for 2. That's great.
Yeah,
now we're going to move on. Looking good. So we're going to go on to our next example. And I'm just going to put up the camera while I explains it.
Okay. So the next sample is cloves. They're in a container. And the question is, we actually prepared 3 different containers. If you were to image multiple, cloves at the same time, you want to look at a bunch of them, then what would be the best container for this? You can use glass, metal, or plastic. You might think that the container really...
Fast and furious.
Nice.
So you might think that the container really doesn't matter because that's not what you're imaging, but X-rays need to get through the container for you to see the clove. So it kind of matters. Okay, so this one actually is more split than I thought it would be, but let's take a look at the results. Okay, so plastic container, 61% was the winner.
Okay, so that's great. Now these, if I just measure this guy, it's smaller than the other one, right? Not as tall, and we're not all the way full of cloves, so we don't need to measure the whole thing. So what I'm going to do is I'm going to put the share back to the other side so you can see the instrument. And I'll just put this back here. We're going to put the sample in. So I'm going to take out the printed, 3D printed block. This is smaller in this case, as I just measured. So I'm just going to put it somewhere in the center, and we can help ourselves a little bit by having a look here. It's somewhat in the center, so it should be good. And we have smaller things, so I've changed the focus to medium. I've left the aluminum filter in, and this is a bit smaller, so we're going to go to 80.
You can actually see the stage move.
That's right. Yeah. If I had that out of the way. So it's a little smaller than that. So we could bring everything in a bit closer. In that case, you can change the geometry completely. You'll see everything moving in even closer, and it's going to change to a 70 millimeter field of view. So in this case, then the detector is actually moving as well. And we can see that if we look right here, just to convince you that in fact, we can move all of these components. Make sure I put my camera back in the right place. And we definitely want to make sure we're centered. So we're going to go to live mode. So, yep. It's just asking me to confirm my dimensions since we changed it from a larger to smaller field of view. Normally, you would measure your sample, you would enter those parameters, and away you go. So here, what we see is our clove bottle. I'm just going to raise it up a tad. Make sure we get lots of cloves in the field of view. And I'm happy with that. So what I'm going to do is just collect a 2-minute data set on this.
I don't think I will be able to guess that those are cloves from this image.
No, it's definitely not obvious that they're cloves from the image. And this, we can look at it from the top and check the progress.
And I guess we're getting a lot of questions.
Yeah. So we've got quite a few that have come in here. So let's start at the top. Stephen asks, going back to the Apple plug. So, and again, we'll get to a lot of the questions at the end. Going back to the Apple plug is the artifacts. Did they arise from shadowing of strong scatterers?
It's not scattering, it's absorption. So it's like photon starvation. It's a metal artifact. And in fact, you can get these in medical x-rays as well if you have implants or something, but it's less of that. It is an absorption effect. Okay.
All right. I think this question came in a couple of times here. So this pre-scan is a 360-degree rotation. Is that correct?
That's correct.
Okay. Let's see another one here. Actually, this is a good one. Why didn't you tilt this one like the others?
Definitely could have. You know, it's a trial and error for sure. Yeah. This one is not as dense as the other. There's a lot of airspace inside, and in fact, the material that's inside is organic. The clothes are. So I didn't feel like I needed to do that. Probably should have tilted the Apple plug though. That would have might have helped.
Yeah. Okay. Another one here is from Joe, and it's can you just run the cloves without the container?
Sure.
So I think we're going to be answering that. We'll be answering that with a little more, Joe. So if you'll be patient for the next scan, you should get a better feel for that. But yes.
I think Joe's measured some X-ray CT data.
I think he's done stuff before. Yes.
Perhaps so, but yeah, you certainly can. Just depends on what you're trying to do. Truly, you're not just going to collect an image. You're going to then go on to analyze that image. And if you wanted to compare lots of different materials together, let's say how cloves differ, then measuring a full container of them is really good. If in fact you're just looking at the structure of clove individually, then maybe one or two is plenty. So you have to ask first, what question am I asking with this CT experiment?
Okay. All right. Okay, we got time for one more question while it's doing a reconstruction. Can we get images of the clove or insects in a vial with ethanol? Right. So, right, in a wet sample, let's call it.
Absolutely, you can, but keep in mind that the liquid is highly absorbing itself. So for example, I've done X-ray scattering experiments where we use a 1 millimeter capillary and put something inside. And it turns out that 75% of the X-rays are absorbed through 1 millimeter capillary. And that's because of the water or the liquid inside. So you want to keep it to a minimum. If you're imaging insects, it really helps if you dry them. And in fact, I would fix them, stain them, dry them, and then image them. So I think later on in the year, we're going to talk about some cases like that that you'll see after the webinar closes. There's also, I think, a handout or a web page that's going to pop up.
Yeah,
oh, we're finished.
I'll be putting those in at the end. So they'll
yep.
come up and then they'll be on the follow-up emails for everybody tomorrow.
All right, so our image is finished. We can zoom in. It's pretty nice. We can see some different phases here. So there's some lighter area inside. The air is dark. We also notice that the material inside is very similar to has absorption similar to our container. And that's because you're 3 for 3 and you've chosen the right condition, the right sample container. What happens, however, if you chose an alternative one that we showed you? Well, for the first one, if you were to choose the metal container, just like you might suspect, you're going to get artifacts, metal artifacts that you can see all around here. Also, the metal is highly absorbing, and we can't see the edge very clearly at all. If instead we use glass, glass is highly absorbing, and it absorbs more than the stuff inside, the organic material, so it appears more faint. Ideally, you want a container that's as X-ray transparent as possible. So no container would be good if we could get them to float into air and stay still. So just to show you those 3 side by side, we have the metal container, the glass container, and the plastic container. And the plastic container is the correct choice. All right, so now we're going to go to our 4th and final sample that Aya is going to introduce.
Okay, so we're going to look at those CLOVES again, but let's say that we want the resolution to be a little bit higher. So what can we do then? So the question for this one is, so which FOV or field of view is best for resolving small features in the CLOVES sample? We're asking this question, which probably makes it obvious, but the field of view and the resolution are related. Okay, this wasn't an easy one. So you got the right answer. 25 millimeters.
All right.
Okay.
Okay, so we're just going to quickly look at that for just a second. So I have the sample that you imaged before, and if I want to go to a smaller sample and I want to move the sample closer to the detector, I need to actually switch containers. So to move from the larger field of view to the smaller one requires a different container. It also requires a different stand. So I hope you can see this. Perhaps if I turn it this way. I no longer want the larger stage. Instead, what I want is I'm just going to take this one out. It's better if you use 2 hands, otherwise I might drop it. So we've got our foam on there. And to hold this guy, I've got another sample stage. It's really easy. It just rotates in. This little disc or rod goes in, it's tightened, and there you go. Our sample's really high now, so we definitely need to bring it down before we go any further. So gonna go back to here. We're gonna switch our shares.
And we do have questions once we get this started, so
okay.
We'll get to those.
Well, I can make some adjustments and you can ask some questions while I do that.
Okay, so let's start with, this is, I think you'll address this as well. So would it be helpful to tap down the sample to prevent potential movement during the scan?
Yeah, or in fact, to wait some period of time.
Okay.
We will cover sample preparation in a sense, and you try to fix a small sample on the sample holder and make sure that it doesn't move during the scan. And we will do a bit more of that next month when we do a high resolution on X-ray CT workshop. Because the higher the resolution is, the more important that the sample doesn't move. When you have sub-micron resolution, the sample moves for 2 microns and it's completely blurred when you get the image. It is important to fix it.
Okay, so yeah, so you just addressed the next question was, how do you know if the sample moved? And that is, it gets blurry, unfortunately.
Mm-hmm. Okay. Like when you take a photograph, if the subject moves real fast, you get a blurred image, right?
Mm-hmm. Like those classical images of the horse or the things running.
Mm-hmm. And nowadays the cameras are so fast that you don't see that too often, I guess, but.
Nope. See, it's moving it even closer.
Mm-hmm.
We know that our height may be wrong. So we're just going to adjust that here. Got to do that every time. Okay, so not bad. Let's rotate it 90 degrees, make sure everything stays in the field of view. And it should, it's pretty narrow. All right, we can move it a tad more if we wanted. Okay, they look like small flowers, don't they? So just to confirm here, we're still sticking with 130 kV. Our focus is still at medium. We're still using that aluminum filter with our 25 millimeter field of view. Now we don't see as many cloves in this case as we did before, but the goal here is optimizing for resolution, optimizing specifically the field of view for resolution. One of the things that I'll just mention, if you can see right behind here, you'll see the last 2 scans that were collected for the 70 millimeter field of view and the 25. But as a consequence of choosing the smaller field of view, our voxel size, or the 3-dimensional size for which we sample our images, is now smaller. And by virtue of that, then that's where we're going to get the gain in resolution. So it's just returning it back to 0. And in the bottom right here, we can see our reconstruction running right there. And, you know, today we're using Rigaku CT Lab HX instrument. We're going to do another one of these where we'll use a different instrument that Aya will be doing next month. I hope you'll join us for that.
All right. Looks like the reconstruction is done, but let's pop in a real quick question while you get that open.
Sure.
Is there a rule of thumb to relate voxel size to resolution?
Yes, there is.
Good question.
That's a good question. So basically, you need at least 2 voxels to see a feature. And a feature could be an edge. It could be part of this, you know, a feature here, let's say, these small voids in here. If that void is 5 microns, then you need at least 2 voxels or 2.5 microns to even see it. But ideally, it should be much smaller, say 1/4 to 1/5 for the voxel size. All right, so you can see here that you guys have chosen the correct answer again. You all get A's. Let's see what happens if you would have chosen a different setting. Okay, so this is the setting with 70 millimeters. We can see things inside, but we can see it's quite blurry. So this is what the 70 millimeter full field of view is, and this is it zoomed in. If we go to 40 millimeters, in this case, we're only seeing the interior of the plastic container, but we are gaining some resolution. It's less fuzzy, and we see some details inside. But finally, if we go to our different container, 25 millimeter field of view, we start to pick up these voids and other details inside. So you might ask, you know, you probably do even better, right? Well, that's our last question. Can we do even better? And it turns out we can. So these are just quick scans to determine, you know, how we should collect the data. If I instead collected this with a 25 millimeter field of view and I use an applied voltage of 90 kV and I used a small focus and collected a little longer, then I pick up some other details. And if I'm still not happy with that, I might optimize some more settings before I go on. So just to review the things we covered really quickly today, we talked about X-ray energy, sample orientation, and we talked about the field of view and sample holder material and resolution. So we covered a few things really quickly, but I hope you got something from this that you enjoyed, you had fun today, and we have some time for some questions.
All right. Thanks, Angela and Aya. We do have time, and obviously we've got a lot of questions that have come in. So we'll start with this first question from Mercury, and he asks, what detector technology are we using? And does it require any cooling? How is just a little bit more basic on the instrument itself?
Yeah, it's a flat panel detector, doesn't require any cooling for the detector itself. We also have used CCDs with lenses for other instruments, but for this one, it's a flat panel detector. We use CMOS detectors as well. So it just depends on the instrument and how you configure it for your laboratory.
Okay, the next two I think are slightly related. So it's, what control over the detector and image settings do you have? So I think that's within the software. And then I think tied into that is, will the focus setting impact the scan time or contrast? And can you speak to those trade-offs of changing those things essentially?
Absolutely, it will. So one of the things I didn't tell you about that final scan is I did say I used a small focus but as a consequence of that, so that you don't burn your target, what you have to do is you have to lower the current setting. So you can stay at 130 applied voltage or 90 kV applied voltage, but the current has to be reduced. And as a consequence, you get fewer X-rays and you get less contrast. So you have to increase the exposure time in those cases. And I think I might not have answered the first question. Did I?
The first question is, can we control those, these settings, right?
And
Absolutely.
also the detector setting, I guess, like a binning and distances.
Absolutely, yes. And you can also, this is doing an automatic reconstruction. You can do this manually, where you can bend 1 by 1, 2 by 2 or greater. It just depends on the sample that you're imaging. And then there's also other reconstruction packages. Some of these have some ways to correct some artifacts. So for like beam hardening or rings and things like that. So there are a lot of things you can do on the detector side.
Okay, all right. We actually had 2 questions come in with respect to fluorescence. Is that a problem, or do you have to reduce the fluorescence from metals? Is that what the filter is doing? So there's an interrelated question of, how do you handle materials that fluoresce?
Well, they would put off some light energy. It depends on your detector material, whether it will measure that. I'm less familiar with the flat panel detectors. I do know that if, for example, you're using a lens-based system where you have a phosphor material, you can pick up fluorescence for sure. But we're not seeing fluorescence to a great degree. So maybe you could comment about the flat panel detector and basically the energy ranges it absorbs.
So either you use flat panel or CCD or SCMOS, and usually they don't have any, or at least not much of energy, discriminating capabilities. So either it's, high energy X-rays you're meaning to use and coming from the X-ray source, or it's usually relatively lower energy that's coming from the sample as X-ray fluorescence. The detector cannot discriminate them, so it will see them both. But fluorescent X-rays, especially when the sample is heavy, the sample probably absorbs most of it. Anything that happens closer to the surface might cause a little bit of a problem. But again, it really depends on the material. For lighter samples, it's probably less of a problem. They wouldn't fluoresce that much. Compton scattering can be a problem sometimes for lighter materials.
Yep.
Okay.
Other X-ray techniques might have to address fluorescence more, say, than X-ray CT does.
But to answer one of the questions that Tom grouped together, the filters we use for X-ray CT are mainly to shift the X-ray energy coming from the X-ray source, not to filter out or shift the fluorescent X-rays coming from the sample. That's at least not the main purpose.
Okay. Okay. So yeah. Okay. So we've got many questions that came in. So one is obviously, is it always best to tilt the sample? Is that really required all the time?
Not always. Had a sample that had some metal in it, and it turns out that to analyze it and to segment voxels for different categories, then it was less optimal to tilt it. But it just really depends. I would recommend that you try a few different settings before you take your final image. If it turns out 2 minutes is great and that's all you need, then that's all you need. But more often than not, you probably are going to measure for an hour or longer.
And you can do a test scan in 2 minutes or even 18 seconds. So
right.
The test doesn't take too long.
Right. We just chose 2 minutes because it gives you some contrast, but you can certainly see a lot in 18 seconds, especially for those heavier materials, the first 2 samples.
And so that comes back to the trial and error part of kind of setting these scans up, right? So
that's right. Absolutely.
Okay.
Got to do a little legwork in the beginning because all of your analysis and quantification of your results after you've collected the image will be impacted by how well you imaged it. So if you don't image it well in the beginning, then your analysis results will be impacted negatively.
Okay. Okay. There's another question is, how did you fix the KV? So that's simply the pull downs, correct? Within the software?
Right. So I can just show you that.
All right. Thank you.
All right, so here's the different settings. And as a consequence, if I change the focus, say, to small, and I'm using a large voltage and I open the shutter, then it's going to adjust down the current so that, we don't melt our target material. So it's intelligent. It knows what it needs to do in those cases. So, but yeah, It's just a drop-down choice.
All right, so we have a couple of questions here. We'll ask them separately, but they are related. Is can you use the device for image construction of hydrated soft tissue?
You can, but as you probably, when I think hydrated tissue, I just see all the water molecules dissolve, evaporating. So you need to make sure that it's in a container where you control that, because for a tissue, you probably have very fine structure. And if it's the water is evaporating, what's happening is your tissue's moving. So absolutely you can. That's why I recommended, but I do recommend you dry it if you can. If you can't, then put it in a sealed container and image it that way. But you can definitely do that. And remember, if it has water in it, that's absorbing X-rays. So you may have to adjust your settings accordingly.
Okay. All right. Boy, we actually had 3 all come in that were very similar there. So let's look at the next one here. Is for a larger sample, is it possible to just focus on a small portion of the sample? So a small field of view that's not influencing the whole thing. And will that increase resolution, reduce testing size? What are some of the trade-offs of doing that type of experiment?
Yeah, it's a good question. You certainly can, but your X-rays are still going through the whole thickness of the material. So a lot of them are being absorbed. Ideally, your field of view and sample size should be closely matched. But if you don't have the choice in cutting or trimming the sample, then you can do that. It's going to require longer measurements. You may have some other undesired effects, but you can do it. The other thing that you have to consider is that when you adjust the FOV, because this is a cone beam and we're using magnification for zoom essentially, then the sample has to move close to the source when you choose a smaller field of view. It's just basically the instrument characteristics. And you have to make sure you can get your sample in and get it close enough. If this was a 100 millimeter sample, we couldn't use a 25 millimeter field of view in this case.
Okay.
Hope that covers what you were thinking.
Okay, so we've had actually several questions come in related to filters. So I'm going to try and amalgamate it into a simpler. Is there a rule of thumb for, let's say, hard samples, polymer samples, mixed samples, for the filter that you would start with, let's say? So for a rock sample, do you normally use, right? Which filter would you normally use? Same thing for a polymer, for a lighter material. Are there any rules of thumbs that can be applied here for getting started, as opposed to playing with the filter, adjusting the filter every time versus
instead of trying 20 different filters
exactly
every time.
Right. Yeah. Yeah. So I would say if you have a material, non-organic, start with an aluminum filter. As the percentage or the composition of metal increases or the density increases, maybe your field of view is growing because you have a large 3D printed object, you might consider moving on to copper. And then we have different widths of copper, different thicknesses rather. So, but I would always start with aluminum if you're using a material sample. And if you're using metals, then maybe you need copper.
Okay.
Any other, well, just before we move on, any other rule
yeah.
of thumb that you have? So Aya's been doing this a lot longer than I have. So let's see if she has
to add just one more category on, if you're looking at organic materials, I would say no filter, maybe like a 40, 60 kV applied. You start from the lower side. But if you have no idea which one to use, I would say aluminum filter, 100, 130 kV is a good place to start.
Yeah.
And when you see the first scan, you will know if you have to go to higher energy side or lower energy side.
Right. So I measured some insects and I was operating, say, in the 50 kV to 90 kV without filters, but that's all organic material. So.
Okay. Here's a question. This one I think is, it might be a bit subjective based on resolution required, is can you differentiate damaged and undamaged substrates, for example, on insects or damaged cloves or grains? And so you can get, looking at identification and diagnosis of those types of that damage, I think. If I'm asking that, I think I'm asking that correctly, yep. Right?
That's, looking at damage and cracks, CT is great for. How you image it and the resolution at which you image it will be impacted by the feature size of that damage. So if it's really small, then you need a small field of view. If it's, if you still can't see it, you can enhance it. So I did an experiment with some carbon fiber reinforced polymer where iodine was used to soak into a crack, and then she could resolve that crack quite easily and look at the orientation of those cracks in 3D. So you certainly can, but it's good to have an idea of how big the damage or the cracks you want to see. And just a quick couple of scans can get you there. Okay. So basically those cracks are filled with air, right? They're voids. Mm-hmm. That's right. So they should be much easier to see against a heavier, denser material.
Okay. The next question is, and this is, I think this is an opinion question, and your thoughts on this, is X-ray microscopy replacing traditional radiography, say example of aircraft components, welded pressure vessels, or would you consider these to still be complementary techniques?
I think we should both answer this one. In my opinion, I think they're complementary. Right. Because let's say that you're on a a factory line and you don't want to slow it down. This is going to slow it down because you're going to have to put it on a stage and rotate it. If in fact you just want 2 90-degree radiographs, shot, shot, move, shot, shot, and you have something to compare it to that can intelligently look at the quality of samples, that's going to work much faster. So it again gets back to what question are you asking from taking this measurement? Are you just quality assessment? Do you want to interrogate internal cracks or damage? So yeah, that would be, I guess, my 2 cents.
Your opinion.
Your thoughts.
my 2 cents. So I think they both have a place.
I pretty much agree with Angela. They are complementary because especially for quality control, when you have to, test many samples in a short amount of time, using X-ray CT is probably not practical. Even if you do a scan in 18 seconds and do reconstruction in, let's say, 10 seconds, that's 20, 30 seconds per sample. And also you have to remember that you end up obtaining, gigabyte size file per sample. And it becomes a question of where are you gonna save all those images? And analysis takes longer, to decide, certain part passed or failed. So for testing of a lot of samples or parts in a short amount of time, definitely regular radiography or 2D imaging makes more sense. But it's good to have a CT capability on the side. And when you see a problem in the radiography testing, that kind of puzzles you and you don't know what you're looking at or what the problem is, then definitely doing an X-ray CT scan would help kind of resolve the problem and answer your question. So I think that those are complementary. They have their own places. In 10, 20 years, when computers get so much faster and we have plenty disk space, it might change, but not today.
Or that article we just saw on the synchrotron collecting data in 100th of
yes,
a second.
that was amazing. Yeah.
Yes.
Wow.
So the technology exists, but you need a very fast sample spinner and you need a very powerful X-ray synchrotron beam line. So when those come to the home lab,
when that happens, right.
Then you can do that. So, okay. All right. I think we're going to wrap up there in terms of questions. So I just want to let everybody know that we do have all of your questions saved and we'll get back to you directly. Okay. So as I said earlier, a recording of this webinar will be available tomorrow and an email will be going out to all registrants with instructions on how to view that presentation. Links to the resources mentioned today, including that new quick reference guide, just went into the chat box. I encourage you to register for our next session, as well as grab that quick reference slide that we put together. And those will also be on the landing page. Finally, we'll be hosting another interactive webinar focusing on the data collection techniques of high resolution CT data collection. Next Wednesday, April the 14th at 2 p.m. Eastern, 11 a.m. Pacific. We look forward to seeing all of you then.
Yep. And that will be another interactive session as well, right, Aya?
Yes.
Yes. So
right.
join us next month.
All right. Thank you all for joining us. And again, we'll hope to see you again in April. Thank you.
Thank you.